Good afternoon, ladies and gentlemen. Thank you for attending our October 15th Improving Talk. We are thrilled you are spending some of your Friday with us. Before we start, I want to inform you about a feature in the presentation that'll make the session a bit more interactive. Please make note of the question mark icon at the upper right of the presentation screen. Clicking that icon will open the question and answer feature, which allows you to send the moderator questions to be delivered to our insightful presenter at the appropriate time. Speaking of insightful presenters, I am proud to present Devlin Liles, who is president of Improving Houston, an author, and someone I feel blessed to call my friend. Today, Devlin will be sharing a webinar titled Artificial Intelligence and Machine Learning, Separating Hype from Reality. The floor is all yours, Devlin.
Thanks, Sherman. And welcome to everybody. We're going to be kind of digging in and talking through this, but before we do, a little bit about myself. For those of you I haven't met, this is just about everything you'll need to know about me. I am a passionate geek when it comes to data, and have been for the last several years kind of constantly confounded by the confusion that AI and machine learning generates, right? From how to use it to how to read every headline and think that, you know, AI-driven robots are going to take over the world. And so what I want to do today is start by talking a little bit about complexity. Now, complexity and difficulty, or complexity and complicated, are often used interchangeably, but we've got to be able to pull those apart to have a really good conversation about AI and machine learning. So complexity is quite literally the number of moving pieces in a system, but it doesn't imply difficulty, right? If I have a 1,000-piece puzzle, it might be very easy to put that puzzle together because the pieces are all numbered and you just put the numbers next to each other. So the number of pieces is complex, but it's not complicated. It's not difficult to assemble, right? Whereas when we talk about complicated or difficulty, some of the simplest things out there, stringed instruments, for instance, you take a cello, you can explain the mechanics and the physics of a cello in just a few minutes. It's only 4 strings. It's got a neck where you adjust finger positions and a bow that causes the strings to vibrate. And it takes lifetimes to truly make it sing. And so when we talk about this, I'm going to be using these terms, difficulty and complexity, as a way to describe the different states of where machine learning are today in different areas. There are some things that machine learning does very easily, even though they're complex. And there's some things that, even though they're simple, not a lot of moving pieces, there's a huge amount of difficulty in them. And so we're going to be using these two terms to separate out hype from reality. Now, the other thing that we're going to be using is the Gartner hype cycle. With most technology, you see this cycle play out in how it's perceived from the mass populace. So there's a technical trigger. This is typically when something becomes possible, right? Like discovery of penicillin was a technical trigger in the history of medication. And then there was all this idea of what it would mean to us. That's the peak of inflated expectations. And then you start realizing all of the difficulties and the complexities of bringing that together, and it becomes a much bigger and bigger problem. And that's kind of where the trough of disillusionment exists. And then that slope of enlightenment is we start producing the first antibiotics and we start treating the first diseases with it. And we realize that we can solve little pieces of this and incremental pieces of this. And then the plateau of productivity is where we have kind of a sustainable and continual process for developing, deploying, and testing the effectiveness of antibiotics. All of that would be the hype cycle for penicillin. Now it gets a lot more difficult when you apply it to specific technologies in today's world, like machine learning and AI, because they're such broad topics. Machine learning and AI cover a gambit of different technologies, different types of intelligence, different applications, and that's where it can get confusing, because in some of them, we're nearing that plateau of productivity or are already on it. And for some of them, we are very much at the peak of inflated expectations. And for some of them, we haven't even gotten to the technical trigger. So let's dive into what those areas are and where it might be effective. Now, as I present some of these things, you're going to probably be thinking about how this applies for you, your office, your work, your industry, or maybe a side project you've been playing around with to predict the winners of this year's baseball October series. Save you a little trouble on that one. I think we know H-Town's going to show up very well. But if you're looking to predict something a little more volatile, this will probably help you out. Now, when we talk about intelligence and learning, we're going to boil it down to very small things. When we talk about machine learning, it is using data to solve a problem, to come up with an answer. Now, what we have done over the last several years is we've been expanding what we define as data. We've been growing that to include pictures, video, GPS data, text, audio files, really kind of anything that can be represented in mathematical terms, we can use as an input into a machine learning model. Whereas the problems we're trying to solve grow ever more complex, like detecting cancer from the pictures of moles, or self-driving cars, or traffic information around optimal routes based on the history of where all the phone's GPSs are. To where do I want to put this grocery store based on the GPS data, demographic data, all pulled together so that I can predict the most likely location that a grocery store will succeed in a given area. Now, as we apply data to solve problems, it becomes this virtuous cycle. Now, machine learning and AI are used together. We use them in the title of this talk together because they're collaborative processes, but they're not interchangeable. When we talk about machine learning, we're going to take data that we've gathered and we're going to have answers. Now, those answers are typically going to come from a human or the outcome of a process. Like we'll have the data for loan applications and we'll have the answers of whether it was a profitable loan for the bank. Or we'll have GPS and location data, but we'll also have the answers of what the most profitable locations for that grocery store were. We'll have all of the player statistics for the 2020, the 2019, the 2018, the 2017 World Series, and then we'll have the winners because those are historical. And we'll compare these two things using machine learning to create a set of rules. Now, those rules are at their base a rules engine, which software developers have been building for years. The only difference is machine learning builds the rules for us rather than us having to write each individual rule and cover each individual edge case. Now, when we do this, those rules can be applied to new data. And that's where AI comes in. We take the rules that we generated through machine learning, we apply them to new data, let's say the 2021 World Series, and we come out with answers, and those answers typically are tied to a confidence level of, I believe this team will win these games at this confidence rate. Or I believe if we put a grocery store at that corner, 70% confident that it'll exceed this amount of revenue in the first 5 years. It's those kinds of answers that drive business decisions. Now, keep in mind, these two don't have to talk to each other. Now, you can make them talk to each other, and we'll talk about that a little bit more later, but at its very basics, this is machine learning and AI as it applies to our world. There are some problems in which writing all of the rules would require 30 or 40 years of experience, would require a ton of documentation and hundreds of thousands of hours of development. But we can feed all of the data and the answers in, and a machine learning model can write those rules in minutes or days rather than years. So as we applied this, these are the constructs that we're going to talk about when we talk about the types of intelligence, because machine learning and AI apply in each of these types. When we train a machine learning model, we're building these layers of intelligence. A lot like how we would raise a child and grow their level of understanding. So that's actually the analogy we're going to use in this. So the first thing is learning, right? The capturing of new information and data. Now, this could be seeing or hearing or feeling or tasting or smelling. Now, as a child, there's not a lot you do with that. Imagine a 2-month-old. They're hearing, they're seeing, they're feeling hundreds of new things every hour, but they don't know what to do with it. It's just information. And so they start manipulating that information. They start reasoning through it, looking for, oh, when my stomach hurts, I'm hungry, I cry, I get fed. Like those kinds of chains of reasoning, right? Oh, when somebody smiles, that's good, but when I see teeth, that's bad. Those kinds of very simple decisions and reasoning start layering on top of it. Now, this isn't enough to deal with complex situations of life yet, but it is enough to start building blocks of forward progress. And then next we look at trying to create results from that information, right? We go, all right, let me look at these pieces together, good. These pieces together, bad. And then we start making more complex pieces, like when I move my arm this way, it doesn't hurt and I can pull myself up. When I move my arm this way, it hurts. Those kinds of fine motor skills start to evolve from different information and the reasoning and understanding behind them. And then we start judging the validity of some of those decisions. I reach out and grab everything in reach. Sometimes I get in trouble, sometimes I don't. And so that kind of understanding of the results allows us to start judging whether I should reach out and grab the glass on the coffee table. Now, as we evolve as children, we start layering these reasoning pieces into everything we do, which is why we see this drastic expansion of the ability to understand complex data from birth to kind of the early 5-6 year range, is because we're layering so much information and they're coming to new truths and new understandings and then layering those into more and more things. Now, as we start doing that, we see relationships between different pieces of information. Oh, there's water on the outside of the glass. That normally means the glass is cold. Those kinds of relationships. Now, as a child, those relationships start very simple. Like that thing is attached to that other thing, right? This piece of the toy is attached to that piece of the toy. My toys go in my toy box is a higher level representation of a relationship. Now, from that, we start to apply truths and that support these relationships, right? Like these are my toys, those are your toys, because my toys stay here, your toys go home with you. Those types of understanding and considering meaning start to show up. And then we start separating what we believe versus what is true. Imagine if you didn't have this step. As a toddler, you learned that crying got you food, right? As a baby. What if you never learned that that was a belief rather than a fact? And at 23, sitting in a college class, you're hungry, so you decide to cry. It doesn't quite work out well. And so we have to start separating what we've learned. Is it either facts, a measurable, observable, and backed by data, observable data, fact, or is it a belief? Is it a logical conclusion that I've seen repeated multiple times, but may only be true right now from my circumstance? And there's so many more layers because each of these starts building back on top of each other. We start treating beliefs as fact and we build these logical chains beyond it. All of this plays into how we as humans grasp intelligence, but it also applies to how computers grasp intelligence. When we talk about capturing new information, that's your systems today. That's how you get data. When you type a search into Google, they're giving you an answer, but you're giving them data. And then they're taking that data and they're reasoning, they're manipulating it, they're looking for relationships, they're trying to grasp truths about you so that they can give you better answers later. And then they're considering the meaning of those different relationships and trying to separate what is true versus what they think is true. All of that so that they can provide better answers to you and better advertising to their customers. So when we see these play out, it's actually very simple to talk through. We just talked through the entire evolution of a machine learning and AI model in about 4 minutes. So why does everybody believe that AI and machine learning are these kind of near mythical proportions, tools and technologies? Unfortunately, it's because of the things they do are very difficult. The things that machine learning does well are typically very difficult for human beings to do well. And the things we do well, machine learning really can't do very well at all. But because we can do those things, we're like, oh, that's not as hard. The things that are hard for us as human beings, we look at machines and they do very well. Like remembering perfectly 4 billion numbers. A computer can do that, no problem. A human being would have a huge struggle with that process. Now, when we apply to machine learning, we say this works, this doesn't. Sorry about that. When we apply to a human being, we say this works and this doesn't. It's pretty easy because you have failures and successes that you can measure against. For computers, we have similar, but this typically comes in longer cycles, right? It takes a long time to build R&D, cameras, test systems, apply it in multiple different genres. So we've broken down some of the types of intelligence and where we're at as an industry with the current AI, right? Current AI meaning that there are tools and there are frameworks that allow you to accomplish these tasks. Visual and spatial, that is the ability for a camera to pick out a person or a cat or a hot dog or another car on the road. We're actually decent at this, like moderate to good. And so there's good potential, there's good tooling. There's actually some pre-built frameworks on AWS, Google, Azure, all to do these things, which means if it's kind of on this chart, if it's moderate to high, it's going to be cheaper and easier to accomplish with your team. And there's probably pre-built tools that you can leverage. Whereas bodily and kinesthetic, we've been doing for years. What this means is controlling physical space, like robotic arms. Now, the more complex the task, the harder this is to do, like getting a robot to balance on 2 legs and walk is a significantly hard thing because it's a mixture of 6 or 7 of these. But robotic control for assembly lines like Tesla, we've been doing with millimeter precision at incredibly fast speeds. So the kind of production automation that we've been doing for years is getting to the point of being able to map these. Some of the most advanced systems that we have in space, like the Canada arm on the International Space Station, actually use models to project, all right, where do I need to move the arms? And it's an incredibly developed system, but it's also several decades old at this point. And so we've been doing this one for a while. There's some very good robotics control systems, flight controllers on drones, those kind of things. So we've gotten very, very good at this. When it comes to creative, it says none. It says none because we don't currently understand how we create new things. Do we create new things, or are we just changing some variables on our own experience? How did Mozart and Beethoven and Bach come up with the music they wrote, right? How do artists create the vision and the emotional evocation that comes from that? We haven't figured it out. And because we haven't figured it out, we haven't figured out how to make a computer do it. Now we've figured out how to make a computer simulate or revise or generate art based on a theme, based on data we've fed into it. But there's no wholly new creation in that. And maybe there's no wholly new creation in what we do either. So awesome, fun way to look philosophically at AI. But for the remainder of this talk, we're going to kind of set that one aside as an R&D topic. Now, when we talk about interpersonal, this is you and me talking. I could be a deep fake and a robot, but that'd be pretty hard if we were having a conversation. But as a video, that's doable now. It's hard. There's got to be enough samples and images and those kind of things of the subject matter, but it's getting better and getting better at a frightening pace. And so we've got the ability to do this. Bots, chats, interactive customer service agents that are largely computer-based at this point allows us to optimize labor, save costs, and provide a better experience for the customer is the goal line. And so these have gotten a lot better. If you're looking at implementing them, there's tons of tools and pre-built services out there for it. And then you get into linguistics, understanding intent and meaning through how somebody speaks or types or writes. That one's a lot harder because sometimes you can say the exact same sentence, but tone and inflection change entirely its meaning, right? have a nice day, or bless your heart here in Texas is one of those. Did they mean bless your heart, or did they mean don't be dumb? That's where linguistics becomes very difficult, because communication is not solely the verbiage, it's the tone, it's the body language, it's all of the things around it. We haven't figured out a great way to make computers good at this yet. And then logical and mathematics, this is where AI shines today. Computers are better at math than most human beings are, because it's a procedural structure and it's based on how they were built. So it works very well. Now, when we look at these types of intelligence and we start mapping them to the things we want to do, right? There's a great image. I actually borrowed it here. It's attributed in the slide of kind of how easy it is to develop. There it is, cost and effort versus kind of the deeper R&D based, more expensive, but much more control of a system. When you talk about vision, speech, language, very easy for normal developers, not data scientists, to dive into and do using current tools, whether that's AutoML, whether that's Azure Machine Learning or Cognitive Services or AWS or Polytopal, or there's a ton out there who are doing really cool things in this space to enable the average developer to accomplish some cool things. Now, if I'm going to have to build my own platform, that's going to be a much more difficult problem. I'm going to need to train my own models, pipe my own data. I'm going to have to build all the baseline pieces that those top services would provide. It's typically more expensive to do. There's a lot of work going on in this space. But this barrier that we talk about between moderate to low is typically the barrier from services to platform, where there's no pre-built frameworks or services to allow us to kind of continue evolving. When you hit that barrier, your costs increase, which means you're going to want to make sure the business value increases there to justify the cost, right? The amount of data, the time and effort it takes to train a model well, the data science required. And then you get into, all right, I'm going to need to have specialized hardware, specialized GPUs. I'm going to need to move terabytes or petabytes or exabytes of data. That's where you're getting into the forefront of AI. Now, when we harken back to the hype cycle, you can look at it this way. Services are on the slope of enlightenment towards that plateau of productivity. Platform is in that trough of disillusionment, where they're realizing the hard parts of all of those pieces and having to wire them together. And anything that's requiring specialized hardware, for me to spin up my own systems to do it, is probably at the peak of inflated expectations, or we're not yet up to the peak. It's on that technical trigger side. This is where hundreds of millions of dollars of AI get spent every year, is in that bottom chunk on trying to make sure that things are possible and then bring them to the mass market. Now, we have oversimplified this, and I don't want anybody to misunderstand. AI and machine learning is a huge space. There's tons and tons of different pieces to this. We're simplifying this whole thing, and there's some things I've said that are true in general, but not true in specific. So as you get deeper into this, we're gonna have available some further learning, some practice, as well as some exploration for product owners, executives, developers. If you email me after this, devlin.liles@improving.com, I'll send you those follow-on links, the learning and reading links as well, so that you can continue to explore this topic if you're interested in it. Now, there's a point that I'd be remiss if I didn't make before we continue on, and that is AI right now is pictured based on what we've seen in the movies. We think Terminator. The problem is, it's a lot more like an idiot robot that's drunk. It'll do exactly what I tell it to. That's not always a good thing. Trying to teach a machine learning model how to evolve legs so you can walk with two legs. It had to traverse 300 meters of obstacles in a virtual environment. Its answer was to create a leg that was 305 meters tall and fall over. Now it's a valid way to solve the problem, but utterly naive. Don't assume Terminator. Assume Bender, because it's going to give you a better understanding of truly what AI is giving us. It's not giving us mythical powers. It's not giving us like magic we can wield at every problem. It's giving us a new tool to solve a very specific set of problems. So I'm going to pause here and see if there's any questions before we move on.
No questions so far, Devlin.
Awesome. Thank you, Shervin. So now I'm going to ask everybody to use your imagination just a little bit. As we use our imagination, there's some common elements that I want you to look for in problems this might be good at solving in your industry or at your company. The common elements of those problems that AI is very good at solving. It's great at performing a very specific task, like estimating the chance that a loan will default. Typically, these are time-consuming tasks because they're worth automating. And it frees up the time on that for the decision, the judgment, the discernment of a human being to be applied. It's not going to say, yes, approve the loan or no. It's going to give input, right? It's going to say, hey, this loan is 60% likely to default because of these factors. At which point a human being is going to be involved and go, okay, that factor doesn't matter in this case. That factor, we can mitigate this other way. Those kinds of things. And we're also going to look for places we can benefit, right? Why do we want self-driving cars? So we can do other things when we're driving in a car, right? Why do we want medical AI? It's typically so we get a better diagnosis, faster, healthier people that live longer. And so when we look at the benefits, don't focus on how we do it today. Look at the outcomes of what if we did it better. That more time to focus on other tasks, a lot of times folks pull back from AI, pull back from automation because of a belief that it will in the long term be a detriment. Think about the ATM. Now the ATM was invented and everybody thought it would be the end of bank tellers. Now, oddly enough, there are more bank tellers today than there were then by a magnitude of 2x. But bank tellers do a very different job. They're not typically doing a ton of manual withdrawals and deposits and balance checks and those kind of things. They're doing other things, right? A banker will also talk about personal finance and those kind of things. We freed up the time to add value. It's not always clean. It's not always immediate, but typically automation and AI cause economic creation on the other end. It just takes some time for it to sort out. Now, once we've identified the common elements and the benefit of what we're looking for, we go, okay, what tasks do I do all the time? Where's most of my time spent? And what would a superhuman version of that look like? And then, can I describe in detail the task? I will say that one of the things I do every day is I do sales for us. I head up our Houston office, and part of that role is sales. Part of sales is staying connected with my network, with the people I've met over time and with the people I care about. I dedicate time to it, but it's very time consuming to go through and try and remember who I'd talked to, who I hadn't talked to, and those kind of things. So what if I had an AI that would tell me, hey, here are some people you haven't talked to in a while, you should probably talk to them. Hey, here's this person who just moved jobs, you should reach out and see how the new job's going. Hey, every February you typically get together with this friend in Northwest Arkansas. Have you booked that trip yet? And it remind me in December. So you start seeing that, okay, the superhuman version of that is I stay connected with the people that I care about, that I've worked with, that are in my network, which is something I want to do, I'm just not very good at. And I can do it in much less time, much less effort, which means I can actually reach more people. I can have more people in those circles. Now, can I describe those tasks in detail? Somewhat, but going through and defining that, emails and text messages and LinkedIn and phone calls and in-person meetings, and I start going through and I kind of capture all the different ways. What's the outcome of it? A deep personal connection between two people. Awesome. What knowledge do they need? Well, they're going to need notes, and the AI is going to need to know birth dates and spouses and kids and parents and brothers and all that fun stuff that you find out as you get to know somebody. And so by doing all of this, I have created the problem space, right, of being able to maintain connections between people. I've also define some of the outputs, right? I want outreach recommendations and calendar reminders and those kind of things. And then I also want inputs, the data I need to perform this. Now, the likelihood is most of us interact with a system like this daily or weekly. It's called LinkedIn. LinkedIn does this. Hey, this person just celebrated their work anniversary. Hit them up. Hey, this person you know just posted something. Go read it. Facebook does this. Most social media systems approach this problem. Now, that's not all to say that they're all great and that they're all valuable and it's not without problems, but there's even some business specific ones that are just focused at the reminders, right? Like Contactually or Outreach.io, that they're purposely built to make sure that people stay connected in the busy and hectic business world that we're in. So I'd love to hear, and if you would, go ahead and use the question and answer pieces of it. And as we continue, Shervin will bring those up when they come in. What are some of the things you imagined? What are some of the tasks that you could see this applying to? Because one of the biggest struggles that we find with AI and ML is most people think it's so big that it can't be applied to small tasks, when actually the opposite is true. A huge amount of value is applied in those small tasks. Now, as you get a chance to bring those up and type those and continue thinking about it, we're going to talk about the language of AI, and we're going to get a little deep into the technical. So I'm going to take off executive Devlin. Hold on a second. There we go. All right. Get the sleeves rolled up, and now I can become technologist Devlin. So when we talk about machine learning, one of the things you'll hear often is a neural network. Now, a neural network sounds really impressive. It's like cognitive brain science, right? Unfortunately, it's actually very simple. It is a connection of data and processes that try and come up to an output. We're going to talk about the different details of this and the language we use to describe it. Now, the factors that come in, these are the things that we're going to feed into the model. In my example earlier about maintaining my connections, this would be my contact list and my activity. Those are kind of the inputs. And then we're going to get predictions like, hey, these are the contacts that you should reach out to based on your contact list and your activities. Now, the weight determines the input, the value of those different inputs. It turns out my activity is really, really important in figuring out who I should reach out to. So it's probably weighted more heavily than my contact list. Now, biases shift the values of those inputs, right? Because let's say that I know that I don't have birthdays for everybody in my contact list. So I'm going to adjust the importance of having a birthday because I know that's a problem, right? This is the data engineering side of it. Another one that you'll often see is like salary surveys. The vast majority of people overstate their salary in surveys. And so when you're running through a bunch of salary analysis AI, you actually adjust that value down slightly based on some statistical modeling on how much somebody reported to how much was reality. Because there's a little bit of kind of overstatement that is built into some of those numbers. And you see this kind of data engineering and maintenance, which we'll dive a lot into here in a little bit, because you need to adjust some of those values coming in. And then the observations, right? These are the things we use to train the data. This is contacts that I've reached out to, I've got activity for, and I can rate the, if I did this manually, here are the 4 people I should reach out to, and compare that to the outputs of the system. Now, when I do that, those observations that here are the 4 people I did manually are going to become part of what it trains the machine learning to create rules that say, here's the patterns that generate those contacts, so that when I add new contacts, they can show up that way. The training data is the data we use to set up the model. And as we develop that model, we're going to test it. That's that test data. Now, both training data and test data are typically heavily manually enhanced. They're manually labeled the data so that I know these are the contacts I reached out to this week, and I marked those. And then I feed those into the model so the model knows how to judge its own assumptions. Now, if we choose to take those outputs and feed them back into the model, it's called backpropagation. It allows the model to kind of grow and evolve as things change over time. There are some systems that don't change pretty heavily, right? And there are some systems where what's important changes regularly. Staying connected with people, contacts, activities, those don't change very often. But what about the job market? What about healthcare? What about housing values? Where what matters has become highly volatile. Backpropagation ensures the longevity of usefulness for a model, but it also creates a problem. As more and more data comes in, it can skew backward the model's decisions. This is unfortunately what we've seen with some of the experiments with chatbots and those kind of things is by backpropagating the user's behaviors, we can make those bots do some pretty terrible things, mostly because people are trying to break the system. And that I'm trying to break you becomes part of the data set that teaches the system. So backpropagation is a big part of machine learning and AI and that virtuous cycle of how they weave together. Now, moving on from here, we're going to take a look at a slightly more complex network. I do want to pause and make sure if there are any questions, Shervin's got a chance to ask them.
We got a few, Devlin.
Awesome.
The first one is, apparently the main AI approach today requires huge amounts of quality data. Would a future machine learning and AI more rely on data or algorithms? Then they also said maybe a related question should be whether you believe that AI development will move forward towards symbolic AI and away from today's connectionist AI. And they do have a follow-up to that question that says, where do you see AI and ML will move in the future? Any chances for a general AI? It's a lot of questions.
Absolutely. So I'm gonna start with the first one of large amounts of quality data. Large amounts of quality data is relative, right? Large amounts of detailed, complex data could be 1,000 records, or it could be billions of records, depending on what you're trying to do with it, right? One of the reasons I bring this up is that we actually teach a machine learning class for developers, and our largest data set is 8,000 records. And it's enough to create functional models. We build, I think, 6 of them in the class over 2 days. What you need is quality data, not quantities of data for certain problems. You need the edge cases, the differentiators, those kind of things. Now, the good news is, for large data set problems, the problems in which the quantity of data is one of the biggest determining factors of the success of the model, there's a lot of business value in companies generating that. And so this is where you'll start to see things like visual and linguistic moving into cloud platforms like Azure, AWS, Google, and you'll see secondary market players who are building on top of those platforms. I mentioned Polytopal earlier, that are building large scale AI that is applicable to multiple data sets because they've had the ability to analyze hundreds of millions of records. Now, when you do that, you can then provide those trained models that are very good across that space, right? When I ask my phone for guidance to somewhere and it listens to my voice, my phone is actually benefiting from the fact that every other voice user out there, that data has been crunched already. Now, there are tons of services in that space that you can leverage, so you don't have to have all your own data. Folks have literally, for millions and millions and millions of records at this point, have audio files and the words that are contained in there in multiple languages. So you may actually not have to create your own data, just have access to a system with great data. The other side of it is, you may have a system that's automatically labeling your data for you. Like if you wanted to look at your most profitable clients, that may not exist in one system, but if you combine 4 systems together, you may actually end up with a profitability level by client with all the additional information that you can feed into a machine learning model. So yes, you need good data. It's not nearly as hard to get, and you don't need nearly as much as most of the time we're talking about. When we talk about trillions of records of data, we're typically talking about the R&D side of machine learning. And you need less and less data to train systems as it moves into that more refined platform, and then again into services. Services, a lot of the times you can train them with very little data and make them productive. Now, where I see AI and ML going forward, and I'm going to skip to the punchline at the end, is that I actually expect to see we've been using AI multiple times for years and years and years. But it's gone through these big peaks and valleys, right? They're called the AI winters, because at one point we hit the capacity of computing power, right? Where computers just weren't strong enough to comp all of the model that we were building mathematically. Now, once computer hardware caught up, we actually had to invent new math, and that caused the second AI winter, where there wasn't a lot of progress. And then we tried to build a general AI and we failed, right? It was just still too complex of a problem. And so we went to building expert systems, specific targeted AI, rules engines, those kind of things that worked very, very well. And we have an entire world built on expert systems today. I believe general AI is in our future. It is somewhere between 2 and 200 years away. And the big question is whether we're going to hit another hard wall in the AI journey before we get to general AI. We may need quantum computing to be prevalent before general AI is possible. We may not. But we don't know what that looks like. Now, for all of those in the audience who are going, what's the difference between general AI and specific? General AI is a set of models and training that is human-like in its ability to adapt to different problem sets. That I could create one kind of global model and apply it to almost any business information with some data. I could apply it to self-driving cars the same way I could apply it to linguistics, to robotics. Specific AI is where we're going to spend the vast amount of time, money, and experience for probably the next 25, 30 years. In combining those, we may start to see commonalities and patterns that we can extract into a general AI core of algorithms that function across the board. But right now, it's very much specific AI. And I actually think that before we get to kind of symbolic AI and those kind of things, we're probably going to have to solve ethical AI and explainable AI. We're going to need to be able to talk about the ethical implications of using machines that are parsing through data that may be biased, that may be corrupt, that may be false. And we're going to talk about some of those pieces here in a little bit and how to protect from them as you approach AI projects. Any other questions?
No, but we did have a comment about, you had asked, where do you see AI and ML being used? And somebody suggested that for 3D printing and doing automatic adjustments throughout the print.
Absolutely. Starting to measure the form and structure of the print and adjust nozzle heat, adjust direction, adjust speed, z-index. There's some really cool video systems and like auto homing systems and auto adjusters for the leveling of the plates that if you interconnected those systems could make 3D printing significantly more accurate. And so you end up with a smoother, better print, but it could also make it faster. We typically have to slow the systems down because the system going slow creates less variation. So we may be able to speed up the entire process once we crack some of those pieces. It's a really good idea. Now, as we talk about more complex neural networks, we also add in some terminology that we want to dig into. The first one is we talk about layers, right? It's a 8-layer neural network, a 37-layer, a 1500-layer neural network. Literally, layers are just the grouping of nodes and how they talk to each other as they move through. It's the boxes on the graph in front of you. Now we have our input layer. That's typically where we feed data into the system, right? Hidden layers are any nodes that get inputs from other layers and don't end up in the output layer. They don't make predictions. They're just adjusting and making additional enhancements to data. They're making subsidiary pieces that are going to feed into additional pieces later. Typically, you'll start from input and you'll build a layer, you'll build more on top of it, and you'll build more on top of it. And that last output and prediction layer, the decision-making layer, kind of continues to move as you grow the network. And then we have our output layer. These are the ones who are actually making predictions based on what we've asked the model. And as we grow the model, what we ask changes over time. Hyperparameters actually control and refine the model. They're things that you have to tell the model doesn't discover. Right? When we feed it data and answers, the model will discover a lot of things. Hyperparameters, however, control what it can discover because they're told to it by the person building the model. And then the model structure is typically how many layers and nodes in each layer, right? 1,500 layers sounds huge until it's like, yeah, but it's one node per layer. Or is it 8 layers with 1,500 nodes? So you start talking about that structure, it's layers and nodes across them. And then division of data. Typically you'll see what's called an 80-20 split, but it's the ratio of training data to testing data used to train the model. And this is where you'll talk about folding and some of those things. Now, when we apply all of this, almost every data model can be developed using a fairly straightforward process. The first steps, the ones that we're going to kind of hop over, but are about 80% of most machine learning and AI projects, are gathering data and preparing that data. That's a lot of work, making sure that it's clean, that it's in one place, that it's been labeled, it's been enhanced, that you've removed bias, mistruth, you've removed invalid data, and then training the model. Now, training the model is actually a loop that happens in the top right corner here. You train it, you test it, you try and make it more accurate, and then you do all of that again. Once you're happy with those answers, you record those settings, you save a trained model, which is effectively that rules engine we talked about earlier, and you start feeding it data. Now, if it's going to backpropagate, you retrain the model on a somewhat regular basis, and then you use that new updated model to continue things forward. But this is the basics of it. Almost every model gets developed this way. Now, in the top right corner, that cycle of training the model and trying to make it more accurate, you may spend hundreds of cycles refining which algorithms you're using, choosing different test data, trying to shape that so that it's creating accurate predictions. But once it's done, this is roughly what it looks like. Now, what do I do with a finished model? I talk to it. Out of code, I talk to it. Typically, you'll put an API on top of it, or you'll embed it in another application or a decision-making system. But the model makes predictions. You still have to end up writing software or handing it off to a human to do something with those predictions. Rarely do we allow machine learning to make decisions entirely outside of human control. We've done some non-human intervention, robotic systems and those kind of things, but they're typically very small cases contained because the risk of not having human oversight in some cases is great. And in other cases, having human oversight actually creates risk. And so that's part of that business model that you want to go through, and you want to model it out and make sure that you've got a plan for how to apply ML and ops to the problem space that you're working on. And we talk about data engineering maintenance. This is where we're going to wrap up, because this is about 80% of most work on an AI ML project. It's prep work. It's making sure that you're ready to do these things. And it's work that you can do today.
Devlin, you muted your presentation.
I muted to cough. My apologies. So we're going to kind of go from past to the future. So the data analysis that we did previously in kind of basic business analysis, data analysis, BI, is very similar to what we do with AI and machine learning. It's just far more complex because the computer can do a lot more work quickly than a human being could do manually. So imagine comparing what you can do in Excel to what a computer with an ML model could do. Right, classical statistics, you can put together some data, you can graph it out, and you get a slope in this case that measures risk of customer churn, right? The amount of money at risk for customer churn. And you get a graph that looks like this, and you go, okay, so based on, driver A and driver B, we've got significant amount at risk at the top of that curve. But if we use machine learning, we can tailor it to specific groupings and structures and clusters of that risk, creating a map that looks like this. Now, one of the things you'll find out is that you see more hotspots, you see more complex data. It's not as intuitive, but it can inform better answers. Now, when we lay these two over it, you see kind of where our true risk lives as compared to where kind of the old BI approach is. This is not to devalue the BI approach. That is identifying some risk and allowing you to make different choices. But when you look at the evolution of ML, you can make far more specific choices. I can go after each of those hotspots with targeted action plans to try and make sure that I don't lose those customers. Now, all of this is based on, everything we've talked about is based on our data being good, clean, and accurate. Data lies, though. Data lies often. We talk about the mistruths of data, right? Mistruths of commission, where somebody actually actively and knowingly enters fraudulent data. Nobody would do that. Give you one of my favorites. I wasn't texting when I got hit. I was totally looking at the road and not down at my phone. Some of those mistruths of commission or omission, where I was never asked if I was on my phone. I just didn't volunteer that information. So when we start running things like cause analysis and feeding insurance data or crash data into a machine learning model to try and predict the safest cars or the worst roads or whatever, we may be muddying the data with behavior from drivers who aren't being entirely forthright. And then you end up with perspective and bias and frame of reference. All of these skew the data we have, and you have to take particular actions to protect against them. So if you're approaching a data project for prep into machine learning and AI, be careful with this one. And if you're looking at it and you're going, I don't know how to protect from all of these, drop me an email. There's a great ebook from Microsoft Press that talks about preparing for ML and data engineering and those practices that I'll send you. And the last thing is, we're getting a lot of data as a world. AI and ML is going to continue to evolve at an incredibly rapid pace because of this. There is so much data available and being generated all the time that we're actually going to be able to continue to leverage it, continue to gain insight and information around health and disease and cancers and traffic patterns and city planning and crop rotation. Like, there's so much data that can make the world a better place, and it's being generated at a massive rate. So one of the things to do is start looking at where your company, your team, your project, your product is generating data, because that's going to be where AI and ML lives. When we look at it, the world as a whole is generating about 0.4 of a yottabyte per year. That's a lot of data. Somebody would even say that's a yotta data. And with that, I'm going to say thank you. I greatly appreciate it. I'm going to hand this back off to Sherv and see if there are any other questions.
Devlin, we do have one. Samir asks, any thoughts on swarm intelligence or evolutionary computation? How important do you believe they will be, and what role will they play in the future?
I think they'll play a massive role in the future. I think there's a lot of interesting things when you look at how society and civilization has evolved, how the intellect of the human race has evolved, and how trying to replicate that into like evolutionary or genetic modeling, those kind of things. It's doing some really cool stuff, but it's also very much on the R&D side of things. Like, we haven't figured out great ways to make that functional because there's so much discovery built into that style of machine learning. It's directed towards a goal, but not to a process. And so it's very much R&D, but there's some impressive applications in the biosciences space. There's some impressive applications in the planning space when you look at like agriculture and those kind of things that I think would be phenomenal if we can bring them to market.
That was our final question.
Awesome.
Thank you all for attending today's virtual Lunch and Learn. And Devlin, thank you for sharing artificial intelligence and machine learning, separating hype from reality. The recording of this session will be available the next business day. To view the recording, locate the session from Improving's virtual events page. And while you're on the virtual events page, be sure to register for future Improving talks. Coming up in November, we have 60 minutes to AWS mastery, secrets of effective time management, and karate more than just API testing. Next week, we won't be having an improving talk on Friday, October the 22nd. We will be away at our annual Las Vegas company retreat, but don't worry, we'll be back on October 29th. Have a wonderful weekend and make sure to cheer for the Houston Astros.